Have you ever looked at a massive bridge or a skyscraper and just thought, how? Why doesn't that whole thing just fall down? What secret forces are holding it all together? Well, today we're going to become engineering detectives and find out. We are diving into the invisible world that keeps our world from falling apart.
Welcome! Today we are cracking the case of the secret strength of stuff. We're going to figure out exactly why things don't break, and I promise we're going to have a blast doing it. Think of it like a science mystery, and you're right here with me, solving the case.
All right, I know what you might be thinking. An engineering textbook? That sounds super complicated, but trust me on this one. We're going to break this all down so simply, it's going to feel like we're just playing with building blocks. Our mission is to make this subject super easy and genuinely fun. I'm talking like explain it to a 10-year-old simple.
So, our guide for this whole adventure is a total classic. We're doing an overview of Chapter 1, called Tension, Compression, and Shear. It's from the legendary textbook Mechanics of Materials by James Gear and Timosenko. We're taking all their brilliant work and turning it into a fast-paced crash course. So buckle up. Okay, let's get right into it. To solve this whole mystery of why stuff doesn't break, we need to meet our two main clues. Their names are stress and strain. Seriously, these two are the key to everything. Once you get them, you will see the world in a whole new way, I promise. So, let's start with two forces you definitely already know. First up, tension. Just picture stretching a rubber band. That pulling? That's tension. And the opposite? Well, that's compression. Imagine squishing a spring or a sponge. That's compression. See? Pulling apart versus squishing together. It's really that simple. And here we go. This is a perfect picture of what engineers are looking at. It's just a simple bar, right? And it's in tension. You see those arrows marked P? Those are the forces pulling on it from both ends. They're trying to stretch this bar out, just like that rubber band. But the real magic is what's happening inside the bar. Okay, so when you pull on that bar, the material inside doesn't just give up. It fights back. And that internal fight, that's what we call stress. You can just think of it as the pressure the material is feeling. The formula is super straightforward. Stress, that's the little Greek letter sigma, is just the force, P, divided by the area, A. It's all about how much force is getting packed into a tiny space. It's literally the material's inner strength.
So if stress is the internal fight, then what's strain? Well, strain is basically just a fancy official word for stretchiness. That's it. It's just a measure of how much the thing actually stretches or deforms. And the formula? Just as easy. Strain, or epsilon, is just the change in length divided by the original length. So think of it this way. Stress is the ouch the material feels, and strain is the actual stretch you can see.
Okay, so materials feel stress and they show strain. We get that. But how do we know how much they can handle before, they snap? For that, we need to check out what I like to call a materials report card. And believe me, this is one of the most important tools an engineer has. And here it is. This chart, this is the stress-strain diagram. But forget the fancy name. Think of this as the entire life story of a material. This single graph tells you everything that happens to, say, a piece of steel, from the very first tug all the way to the final dramatic moment it breaks. Let's walk through its life story. So, let's follow the plot. At first, in this straight-lined part, the steel stretches, but if we let go, poof, it bounces right back to its original shape. But then it hits the yield point. This is the big one, the point of no return. The steel is now permanently bent. If we keep pulling, it gets to its ultimate stress. This is the absolute maximum fight it has in it, before finally, it fractures, it breaks. The end. You know what's cool is that different materials have totally different personalities. Over on the left, you've got your ductile materials, like steel. They stretch and stretch and stretch, giving you tons of warning before they finally fail. It's kind of like they're yelling, "Hey, I'm struggling over here." But then on the right, you have brittle materials, like glass. They show almost no stretch at all. They just snap, gone, no warning whatsoever. And this whole idea boils down to two key behaviors. First, there's elastic behavior. That's when something bounces right back to its original shape, like a rubber band. It's like it has a perfect memory. Then there's plastic behavior. That's when it stays bent for good, like when you mess with a paperclip. It's basically permanent. It's like the material gets amnesia and forgets its original shape. And this chart shows that difference perfectly. Look on the left. We pull the material a bit, then we let go. The line goes up, and then right back down to zero.
perfectly elastic. It's basically saying, ta-da, I'm back. Now look at the right. This time we pull it past that yield point. When we let go, look, it doesn't go back to zero. It's permanently stretched now. That's plastic. It's like it's saying, yeah, I'm never going to be the same again.
All right, on to our next big clue. We've covered pulling and squishing, right? But what about a cutting force? This is where shear comes in. And trust me, it's a force you actually use every single day, probably without even thinking about it. So, shear stress is basically a sliding, slicing force. The best example? Scissors. The two blades slide right past each other to cut the paper. That is shear. It's totally different from tension and compression, which act head-on. Shear acts parallel to the surface. Its symbol is the Greek letter tau. Yeah, it's kind of like the ninja of forces.
And here is a perfect real-world example of that. You see this bolt holding two plates together? The plates are being pulled in opposite directions. So what's happening to the poor bolt in the middle? Those forces are trying to slice it clean in half. You can literally see how the forces are trying to shear it. That is a textbook case of what we call direct shear. And this exact thing is happening in bridges and cars and buildings all around us, all the time.
Okay, so we've got stress, strain, and shear down. Pretty cool, right? But how do engineers take all this knowledge and actually build things that don't fall down? Well, it all comes down to one golden rule. Seriously, this is the rule that keeps you safe every single day.
And that rule is called the factor of safety. This might be the single most important idea for keeping us all safe. It's actually a pretty simple ratio. All you do is take the real, ultimate strength of a material and divide it by the strength it needs to have for its job. It's like building in a giant safety net, just in case. So what does that actually look like? Well, imagine an elevator cable needs to hold 1,000 pounds. An engineer might decide to use a factor of safety of, say, 2.0. That means they will use a cable that can actually hold 2,000 pounds. It's literally designed to be twice as strong as it ever needs to be. That's the safety buffer. And that's exactly why you can step into an elevator and feel safe.
All right, you've been listening, right? Time for a quick pop quiz. Which term describes that internal pressure, that fight, a material feels when you pull on it? Is it A, strain, B, stress, or C, shear? Think about it. Lock in your answer.
And the answer is B, stress. That's it. Stress is the internal force fighting back. Remember, strain is the actual physical stretch. Awesome job. See? You're already thinking like an engineer.
Okay, let's do a super quick wrap-up. Here are the key things to remember. Stress is the internal force. Strain is the stretch. That stress-strain diagram, it's the material's report card. Ductile materials bend, brittle materials snap. Shear is a slicing force. And the big one, the factor of safety, is how engineers make sure things don't break. You basically just learned the secret code of how our entire world is built.
And that's a wrap on this investigation. Hey, if you found this useful, do me a favor and hit that like button. And if not, that's cool too. Hit dislike. We want to know. Definitely drop any questions or comments you have below. Oh, and make sure you follow, because our next explainer is going to be a deep dive into section 1.2, normal stress and strain. You are not going to want to miss that. Thanks for hanging out, and I'll see you in the next one.